Now that you're familiar with exponential and logarithmic functions, we need to discuss how you would solve an exponential or logarithmic equation. Now there's two primary ways of doing this. And they're using the two properties that we've already discussed earlier, but we're going to discuss them in a little bit more detail now. They're the one-to-one property and the inverse property. Now, you'll probably use the inverse property more than the one-to-one property, but we really could use either one depending on the setup of the exponential or logarithmic equation. So the one-to-one property. Because exponentials and logs are one-to-one functions, they have this one-to-one property, and that is for exponentials. If I have two exponentials equal to one another, if the bases are equal, so in this case they're both a, if my bases are equal, then the exponents also have to be equal. So x has to equal y. Same thing for two logarithms. If I have two logarithms that are equal to one another, if the bases for each logarithm are equal to one another, then the things inside the logarithm also have to be equal to one another. And that's due to the fact that these are one-to-one functions. Then you have the inverse properties for both exponentials and logs, and this is the idea of compositions and inverses. If I take f of f inverse of x and I do this composition, I should just get x. We think of them like the two functions cancel each other out. So if I take an exponential function here and I plug it into a logarithm with the same base, then we would think that these two functions would like cancel each other out and I would just be left with x. And it's not direct canceling like you would cancel common factors in a fraction, but you can think of it like they cancel. It's more of a property of inverses though. Same thing here. If I have an exponential function and I take a logarithm and I plug it into the exponential, which means put it in the exponent, then since these have the same base, I could say these things are the inverse, they'll cancel, and I'll just be left with x. So these are the properties we're going to primarily use to solve exponential and logarithmic equations. So let's look at a couple. So here's a couple of exponential equations. So 2 to the x equals 32. Now there's a couple of ways you could solve this. One way is you could just ask yourself 2 to what power gives me 32? And you might come up with the answer of x equals 5. Alright, but what's a more systematic way of doing it? And one more systematic way of doing it would be to use this one-to-one property. The idea is if I could take 32 and write it as 2 to a power, then I have two exponentials equal to one another where their bases are the same and therefore their exponents have to be the same. Well, I could do that. 2 to the x equals 32. 32 is 2 to the fifth. So since I have two exponentials equal to one another and their bases are equal, their exponents have to be equal and therefore x equals 5. Let's do the same thing here for this one. 1/3 to the x equals 9. Again, I can use the one-to-one property here. If I can somehow make the base on each side be the same, I could set their exponents equal. So 1/3 to the x. I could write 1/3 to the x as 1/3 to the x, which is the same thing as 3 to the negative x. So then 9 we know we can write as 3 squared. So what I get is 3 to the negative x equals 3 squared. The bases are the same, so the exponents, negative x has to equal 2, so x equals negative 2. And you might be able to just come up with that answer by looking at this and say, what do I raise 1/3 to get 9? But this is again a more systematic way of doing it. But the problem is that doesn't always work. Let's say this number right here was 31. Well, if that number is 31 instead of 32, I can't write that as 2 to a power, and then the one-to-one property won't work because I can't get this. Same thing here. If this was, say, a half to the x equals 9, I can't get the bases on each side to be the same, 3 and 3. So the one-to-one property has its limitations, and that's where we're going to come in with the inverse property. Here's this next one. E to the x equals 7. It has roughly the same form as these other two. If you look at these other two, if I make some room here, if you look at these other two, there's something raised to the x power equals a number. That's all I have here. Some base to the x power equals a number. The only problem with this one is I can't take 7 and write it as e to a power and then set my two powers equal. So the one-to-one property just stops working at this point. And it's very rare that the one-to-one property actually will work. I mean, these numbers have to be set up exactly right for the one-to-one property to work. So then we're going to think about how this inverse property works. The idea is when you're trying to solve an equation, in this case we're trying to solve for x, we want to figure out what x equals. We want to get x by itself. And normally when you solve for x, you want a 1 as its coefficient and a 1 as its power. And then what it's equal to can't have any x's in it. And if we can somehow take this equation and put it in that form, then we solved it. Well, in order to do that, I need to get rid of this e so I can get x by itself. So I look at this here and I go, okay, how can I get rid of that e? Well, if I use my inverse property, and this is an exponential, so if I plug this exponential into a logarithm, like I could here, I could cancel out these two things and just get the x. But I got to pick the right logarithm. This is base e, so I need to use a logarithm base e. So if I took the natural log of e to the x, then the natural log and the e should cancel and I can get x by itself. Now I can't just do that. However, this is an equation and you have rules for equation that say whatever you do to one side of the equation, as long as you do it to the other side, you can do it. So in this case, I'm going to just take the natural log of the other side as well. And what happens is these two will cancel. I'll get x equals natural log of 7. And I could have done the same thing with these other two examples as well, but these were easier to be done with the one-to-one property. But again, that one-to-one property just doesn't work all the time, and really rarely will it work. It has to be set up very nicely for that to work. So you're going to be using this inverse property in most cases. Let's see a couple of log equations now. So those were 3 exponential equations. Here's 3 log equations. So again, you either use the one-to-one property or the inverse property. So this first one, what we're going to do is we're going to use the one-to-one property. I'm going to rewrite this equation as the natural log of x equals natural log of 3. I'm just going to move this natural log of 3 to the other side by adding it, and I get this equation. Now this is the one-to-one property in that I have 2 logs equal to one another, and those logs have the same base. They're both natural logs. So that means the thing inside the logs have to be equal, and I'm done. Again, that's not going to work out so well all the time. It has to be a very nice setup equation for that one-to-one to work. So most of the time you're going to be using the inverse property. Now the inverse property we'll use for these two. Now the thing is, you have a log, so you need to introduce an exponential. Remember, a to the log base a of x equals x. So if I have a log and I put that in the exponent of an exponential with the same base, I can get these to cancel and just give me the x. So if I look at this one, the natural log of x equals negative 3. If I used e to the natural log of x, this is an exponential with the same base as this logarithm, and these should cancel. Well, if I do that on one side, basically take this side and put it in the exponent for a base e, I'll just do the same thing on the other side. So what I get is x equals e to the negative 3, or 1 over e cubed. And that solves me for x. Let's try this next one. Log base 10 of x equals negative 1. So if I take an exponential with the same base, in this case 10, and I raise this side to that exponential, I'll just do the same thing to the other side. These will cancel. I'll get x equals 10 to the negative 1, or 1 over 10. So there's my solution. So this is how we're going to solve these. One-to-one property sometimes, but most of the time you can use that inverse property. And essentially I could tell you, really, you could use the inverse property for every single one and never use the one-to-one property. But sometimes it is just easier to use the one-to-one property. This process of using the inverse property for these, where you put these sides into the exponent for an exponential, it's called exponentiating your equation. So this should be your strategy when it comes to solving these types of equations. The key, and this is the most important part, is you need to isolate your function first. If you have an exponential function that you're working with in your equation, get that by itself on one side of the equation first. Like we have e to the x equals 7. This is by itself on this side of the equation. Get your function by itself, isolate it. If it's a log, same thing. Log base 10 of x equals 7. This log is by itself. If it's not by itself, get it by itself first. That's going to be a major key, because if you don't, it's going to be so much harder to solve the equations. After you do that, look to see if you can use the one-to-one property. Again, not going to happen a lot, but if you can, it's fairly easy to work with. And the idea is, can I get the same log on both sides? Can I get the same exponential on both sides? And most times that's not going to happen, but just check to see if that'll work first for some special examples. If that doesn't work, then if you have an exponential equation, then you can use the inverse property by writing it in log form. Or if you have a log equation, you can exponentiate both sides, and you can write the inverse property for that. So essentially these are the same thing. Use the inverse property after you try and see if the one-to-one property works. But this is a key to solving these equations. Isolate your function first. Alright, so here's a couple more exponential equations. So first one, 4 to the x equals 72. So look at this, 4 to the x equals 72. The question is, first, is my exponential isolated? Yes, it's by itself. 2, can I use the one-to-one property? Can I write 72 as 4 to a power? And if you think about it for 2 seconds and can't come up with it, then go right down to the inverse property. Because in this case, 72 can. But don't spend a whole lot of time trying to use the one-to-one property, but just look at it real quick. One-to-one property won't work. So now inverse property. Inverse property is, I'm going to try and get rid of this 4 so the x is by itself. How? I'm going to take the log base 4 of 4 to the x. Well, I'll just do log base 4 of 72 as well. And that tells me that these will cancel. X equals log base 4 of 72. And that's it. You're done. If you could simplify it more, you might want to, but I'm fine. Just leave it like that. And there's your answer. Let's do the next one. 3 times 2 to the x equals 42. First, isolate the exponential. It's not isolated. Get rid of this 3. Divide. You get 2 to the x, divide 42 by 3, and you get, what's that, 14? Now, does the one-to-one property work? Can I write 14 as 2 to a power? No. Use the inverse property. So I'm going to take log base 2 of 2 to the x equals log base 2 of 14. These cancel. X equals log base 2 of 14. Done. Next one. E to the x plus 5 equals 60. Is the exponential isolated? No. Get rid of the 5. Subtract. Move it to the other side. E to the x equals 55. Can I write 55 as e to the x? No. So one-to-one property doesn't work. Go to the inverse property. Take the natural log of e to the x. I have to use natural log because remember, the bases have to be the same. This was base 2, I used base 2. This was base 4, I used base 4. This is base e, I got to use a base e. So I get the natural log of 55 on the other side. These cancel. X equals the natural log of 55. Done. One more. Let's put it here. 2 times 3 to the 2t minus 5 minus 4 equals 11. Is the exponential isolated? No. So what do I got to do? Add 4, divide by 2. Add 4, I get 15. Divide by 2, I get 15 over 2. So I get 3 to the 2t minus 5 equals 15 over 2. Now get rid of the 3. How? With a logarithm. Log base 3 of 3 to the 2t minus 5 equals log base 3 of 15 over 2. These cancel, and I get 2t minus 5 equals log base 3 of 15 over 2. Now remember, you want to solve for your variable. And this isn't solved for yet. Usually we get to the point where at this point our variable is by itself. Our variable is not by itself here. So now I got to simplify a little bit more. I'm going to add 5, divide by 2, and I get t equals log base 3 of 15 minus log base 3 of 2 plus 5 all over 2. Now, you might say, where did this come from? Well, this is a quotient inside my logarithm. So, quotients can turn into subtraction, so I wrote it like this. I didn't have to do that, but just to get you practice, you're going to see that a lot, so I wanted to show it to you. So this is now my solution. But the whole point was that you had to use the inverse property to get our answer. Okay, here are a couple log equations now. Same deal. Get your log by itself. So here, natural log of x equals 3. Log is by itself. I can't write this as a log, so I'm going to get rid of the log instead. How? Inverse property. E to the natural log of x. I raise this into the exponent. Equals e to the third. These cancel. X equals e to the third. Next one. This one, we can use the one-to-one property. If you look at it, it's got one log equal to another log. The bases are the same. So this is a case where the one-to-one property does work. In every rare occasions, it will work. So look at this. I'm not going to try and do an inverse property here. I can just set these things, 5x minus 1 equal to x plus 7, and solve for x. Well, if I subtract x, I get 4x. I add 1, I get 8. X equals 2. There's my answer. Next one. Is my log by itself? No. So get the log by itself first. I'll subtract 5, divide by 2. So I end up with natural log of x equals, what would it be, negative 1/2. Now that the log's by itself, I can't use the one-to-one property because I don't have a log over here. So then what I'm going to do is use my inverse property. E to the natural log of x equals e to the negative 1/2. So these will cancel, and x equals e to the negative 1/2. Now here's something that you might see, so I'm just going to do it. This is the same thing as 1 over e to the 1/2. But remember, e to the 1/2 is the square root of e. And that's a root in a denominator. You should have learned in algebra you can't have roots in a denominator. So now I'm going to rationalize it. Square root of e over the square root of e. And I end up with the square root of e over e. And that's my solution for x. That might have been taking things a little too far. I mean, this I think is acceptable, but you're going to see stuff like this, so you should know how to do it. They're the same answer, but this is probably the better answer. All right, one more. 2 log base 5 of 3x equals 4. The log's not by itself. I got to get rid of this 2, so I'll move it over by dividing. So then I get log base 5 of 3x equals 2. Now I want to get rid of the log, so I'll do 5 to the log base 5 of 3x equals 5 to the second. Do it on both sides. That then gives me, these cancel, 3x equals 25. So x equals 25 over 3. Now there's one thing that you're going to have to worry about when it comes to these equations. Exponentials, if you remember exponential functions, the domain for an exponential function is all real numbers. The domain is anything. But logarithms is a different story. Logarithms have a limited domain in that you can only take the log of a positive value. So one thing you have to do when it comes to the log equations is you're going to have to check your answer anytime you have a function that has a limited domain. Square root equations, log equations, equations with fractions in them. These are all types of functions that have limited domains. So what you're going to have to do is always check your answer for those types of equations, and this is one of them. What you're looking for here is, can I do this? Can I, if x is e to the third here, if I plug e to the third in here, can I do that? Can I take the log of e to the third? Well, as long as it's a positive value, yes, you can. So that's fine. Look at this one. If I plug 2 in here and here for x, will I be taking the log of a positive value? Well, if I take 2 in there, I'm going to get 10 minus 1 is 9. Yes, I can take the log of 9. If I plug 2 in here, I'm going to get 9. Yes, I can take the log of 9. So that's fine. Those will be a solution. We're good there. Same thing with this one. This is a positive value. If I plug it in here and I multiply it by 3, it's still positive, so I can do that. This one's 25 over 3. If I plug it in here, I get 3 times that, positive, so I can take the log of that value. Okay, these check out. But that's not always going to happen. I'm going to show you an example that where it's not going to work out. Okay, here's one where I'm going to solve it just like I normally would. Now this one's got some issues that you're going to come across, so this is a good example for a couple of reasons. Your first thing you always look to do is isolate your logarithm. The problem is I have 2 logarithms. The nice thing is they're the same base, but I have 2 logarithms. Now I can't just move this log to this side here and then have one log equal to another log because I got this 2. So what I need to do is I need to take these logs and I need to condense them into a single log, which I can do because they're added together and they have the same base. So what I'm going to do here is I'm going to write this side as log base 10 of 5x times x minus 1 equals 2. If they're added together, the things inside should be multiplied together. Now I got it to the point where I have a single log equals something. The log is by itself. I can't write this as a log, so I'm going to get rid of the log instead with the inverse property. It's base 10, so I'm going to do 10 to the log base 10 of 5x times x minus 1 equals 10 to the second. These cancel. I get 5x times x minus 1 equals 100. And I solve this equation for x. Well, look at what this equation turns out to be. 5x squared minus 5x equals 100. It's a quadratic equation. So then you got to think to yourself, how do you solve a quadratic equation? You have factoring as an option. Quadratic formula is an option. Completing the square is an option. Choose one that you think fits this best. I'm going to try and factor it because that's usually the easiest. I have to set it equal to 0. I'll factor out a 5. And then I can write this as x. What's it going to be? I got to get a negative. So x minus 5, x plus 4. That gives me negative 20 and negative 1 here and here. So then we go, all right, my solution is x equals 5 or x equals negative 4. Now, this is the problem. It's a log equation. Make sure you check your answer. If I plug 5 in here for x and here for x, I'll get 25 and I'll get 4. I can do those fine, so this is good. That gives me positive values. Okay? But if I plug negative 4 in here and here, one of these just has to be negative, and in fact both of them give me negatives. Let me erase some of this so you can start seeing what the equation was. Okay, if I plug negative 4 in here, I'm going to get negative 20. I plug negative 4 in here, I'm going to get negative 5. They're both negatives. I can't take the log of a negative, which means this can't be a solution. So we call this thing an extraneous solution, which is a bad sort of name, I think, because it makes it still sound like it's a solution. But an extraneous solution means it's not a solution. You solved everything right. Everything we did was right, but what we came up with doesn't work in the original equation. So this would be my only solution. And this is the reason why you're going to have to check your answer. Lots of times you're not going to come up with an extraneous solution unless you do what we did here, which is we brought these two logs together as a single log. That's largely the time where you're going to have to worry about this, but you really should check all your answers when it comes to log equations. So here's a slightly more difficult exponential equation too. So this exponential equation has more than one exponential function in it. Now, one thing you might have learned, or I mean should have learned, but I don't know, maybe it got skipped, but you should have learned solving equations through substitution in algebra. And the idea is I can take an equation and I can rewrite it as a different type of equation if I pick a particular substitution. And that's what we're going to do here. I can't get the exponential by itself. I have two of them. I have e to the 2x and e to the x. And I can't just get this as one e to the power function, and I can't get it by itself. I also can't get e equals e to a power and set those powers equal to one another because of this 2. So what I'm going to do is I'm going to use some substitution, and there's a trick to this, and the trick is this. E to the 2x is e to the x squared. Because if you have a power to a power, you should multiply these exponents, and that would give me e to the 2x. If that's the case, this equation is e to the x squared minus 3 e to the x plus 2 equals 0. And if I pull this e to the x out, this is just going to look like a quadratic. So if I say, let's let u equal e to the x, then what happens is I end up with u squared minus 3u plus 2 equals 0. That's a quadratic that is very easy to solve. I can factor it. I get u minus 2, u minus 1, which tells me u equals 2 and u equals 1. Which is all great. Okay, I know what u equals, but this equation was an x. And I really want to know, when it says solve, it really means solve for the variable. In this case, solve for x. We solve for u. So whenever you do this substitution, what you're going to have to do is say, all right, I don't really know what my variable I'm looking for is equal to yet. But what I can do is use my substitution equation. And I could say, all right, well, if u equals e to the x and I know u equals 2, if we use this u equals e to the x, I can figure out that 2 equals e to the x. And that's an exponential equation. I'm going to say the natural log of 2 equals x. And there's my answer. But that's only for one of those u's. Here's another u. If I use u equals e to the x here, I can say, okay, 1 equals e to the x. So if I take the natural log of 1 equals the natural log of e to the x, these cancel, I get natural log of 1 equals x. There's my other answer. But remember, natural log of 1 equals what? Natural log of 1 equals 0. So this is the same thing as x equals 0 is my other solution. So here's one solution, here's another solution. Now I don't have to check these answers because this is an exponential equation. And there's no problem when it comes to exponentials as far as their domain goes. The domain is all real numbers. So sometimes you'll come across these harder exponential log equations and you still need to solve them. Largely the key is to get it to the point where you just get an exponential equals a number or a log equals a number, so isolate your function. But sometimes you need to use some of the tricks you learned along the way in algebra or even some of the properties of logarithms. Alright, so now that we know how to solve equations with logs and exponentials, we can do a very quick application. We did compound interest formulas. And essentially what we have here is another compound interest problem. But it's asking for something different. Rather than asking how much I'll have in the end, okay, This is asking how long it will take to get a certain amount. So how long will it take for an investment of $500 to double if the interest were compounded continuously at 6.75%? Well, your compound interest for continuously compounded interest is this formula. It's your PERT formula. A equals P times e to the RT. A is the final amount. That's just sloppy. All right, let's try that again. Final amount. P is your principal. We'll say that's the same thing as starting amount. R is your rate. Remember, write as a decimal, not percent. And T is time. Time in years. So I want to start with 500. I want it to double. So I want to end with 1,000. So A is 1,000. P is 500. E is just E. It's a number, right? That's not a variable. R is my rate. So if I turn this into a decimal, it's going to be 0.0675. You just move it 2 decimal places to get rid of the percent. And then I have T, which is what I'm looking for. How long will it take? Time. So I need to solve for T. T is a variable in the exponent. This is an exponential equation. So I'll isolate the exponential. I gotta get rid of the 500. I'll divide by 500. So if I divide by 500, I want to get 2 equals e to the 0.0675 t. Now I got to get rid of the e, so I'll take the natural log. Divide by 0.0675. And I get my t. So t equals the natural log of 2 over 0.0675. Which is technically the answer, but does that really tell you how long it is, how much time it is in years? Probably not. So now you want to go to your calculator. So I'm coming up with 10.27 years. So roughly 10.25 years, right? And then this is an estimate, so I really shouldn't put equals. I should say this is roughly 10.27 years. But that's how long it's going to take for your money to double. Even if you want to estimate, say roughly 10 years, right? 10 years it's going to take for me to get $500 to double to $1,000 if I have continuously compounded interest at 6.75%. That's a long time. Okay, I know for me to get my 500 to turn to 1,000, I don't know that I could wait 10 years for that, but that's how interest works, right? 6.75% is also a pretty high interest rate compared to what you'll probably get nowadays. All right, so now you know how to solve log and exponential equations.